Hello everybody. The topic which I want to explain you in this video is about the properties of laser beams. So let me put the heading as properties of laser beams. So we know that a laser has got three important parts in it. The first one is called active medium, which I'm going to abbreviate as AM inside this box here, active medium. And to achieve something called population inversion inside this active medium, we use something called pumping source. That's I'm going to abbreviate as PS. And to actually kind of amplify the photon flux inside the active medium further, we use feedback mirrors. The left one 100% reflecting, and the right one maybe 99.9% reflecting. That means a part of the laser, the light which is oscillating inside this laser cavity we call is actually kind of leaks through the right hand of the laser. So this is actually the important parts, and if you actually kind of observe the output of this laser beam with the help of something called a spectrum analyzer, then you will be able to get a graph or a plot of intensity of the laser uh, as a function of wavelength of the waves which are present inside the laser output, and that graph is usually narrow. Let me put something like this. So it is usually narrow for the case of lasers called continuous wave lasers, CW, continuous wave CW lasers. And of course this width could be actually kind of more for pulsar lasers. So anyways, if you observe the conventional the output of the first laser, which is a ruby laser, it is actually kind of very narrow in width in the domain of wavelength. So we can say that output of laser beams is actually highly monochromatic. So the first property which we can actually kind of discuss is monochromaticity of the laser beams, and that's actually usually high when you compare this is called spectrum actually. So when you compare the spectrum of laser output to the spectrum of some incandescent bulb, laser output is pretty monochromatic. That means it will have only a single color coming out, but with a small spread of wavelengths around the primary wavelength. Uh, Whereas for the case of incandescent bulb, we get some spectrum like the black body spectrum, uh, which is very broad in wavelengths. So anyways, this monochromaticity is coming because of involvement of two fixed energy levels, E1 and E2 energies, or the energy level, energies of those levels. And when we discussed about the laser principle, we said that we'll be having absorption of lasing photons between these two levels, and stimulated emission of lasing photons um, between these two levels, which actually kind of contribute for the amplification of lasing photons. So the laser frequency, the frequency of the lasing photons can be written as nu is equals to E2 minus E1 divided by H. And when E2 and E1 are fixed, this nu is also fixed, and we know that wavelength of light is actually c by nu. So when nu is fixed, even lambda is fixed. That's why we'll get a single lambda coming out of the laser. So yeah, this is one of the reasons, and the other reasons is this arrangement of the mirrors is actually kind of fixed. That means the distance between the left mirror and the right mirror is actually kind of a constant. And if we assume that constant as L, then we know that laser cavity, we call this arrangement as cavity. Laser cavity will support only the wavelength, which is actually C by, let me put the resonance condition, which is some integer n into lambda, which is actually kind of wavelength of the light which is inside. So n into lambda by 2 should be equal to L. So for the longitudinal mode support, we need this equation satisfied. So only the wavelength which is coming out of this one as a spike will be supported, but any kind of waves which are actually having wavelength slightly lesser and slightly more will be actually suppressed by the resonance condition, this condition inside this laser cavity. So that's the reason why we actually get a monochromatic laser output. And let me go into the second property of the laser beams, that's actually coherence. So we know that light is transverse electromagnetic wave, and if you actually kind of draw the electric field of light wave as a function of either time or maybe space, so we can designate that as a kind of a sine wave like this. And we know, if you call this as theta axis and this as electric field axis, then we can actually kind of say that E is going something like sine theta function, where theta could be actually either spatial, involving spatial coordinate or maybe temporal coordinate. So this theta is actually usually called as the phase of the wave, phase. So and we also know that if the laser beam is coming like this, then at some point or on some surface involving the laser beam, we'll have this phase as a constant value. That means, let me define that. So it is actually a surface which has got equiphase surface. Equiphase surface is actually called as a wavefront. So this one is called as wavefront, and if this equiphase surface, which is also called as wavefront, is actually a plane, then we call that we are dealing with a plane wave of laser beam. And if this wavefront is actually kind of a spherical surface, then we say that we are dealing with spherical waves. So anyways, this is the one. But in a laser beam, if you pick up 2 points, let me say point number 1 here and point number 2 here, and at these 2 points, if you actually kind of consider the phases as theta 1 and theta 2, and if the difference of theta 1 and theta 2 is actually kind of constant, theta 1 minus theta 2, if it is a constant value for all times, then we say that we are having something called let me put a second here and let me write this coherence. We are having especially spatial coherence. So in space we have got spatial coherence. So if you pick up 2 points, point number 1, point number 2, and if you call the phases at those points as theta 1, theta 2, and if the difference of them is constant, then we say that we are having spatial coherence, at least partial spatial coherence. And if we take any 2 points in the laser beams, which could be actually kind of nearby or maybe very far away, And if we achieve this condition, theta 1 minus theta 2 is equals to constant, then we say that we are having perfect spatial coherence. And usually it won't happen, but the area around the points where we have got spatial coherence is actually called as coherence area. So this is about coherence, which deals with phases and the difference of the phases between 2 points. So anyways, so far we discussed about spatial coherence, but similarly we can also discuss about something called temporal coherence. So let me write that first, temporal coherence. So this should be actually B, because we considered the spatial coherence as A, so this is actually small b here. So for the case of the spatial coherence, we have taken two different points in space. Now for the case of temporal coherence, we only take one point in space, and at that point we actually consider the phases at two different times. First one could be at time theta sub t, and second one could be at time theta at time t and plus some tau. So after some time tau, if we observe the phases at time t and at a time t plus tau, then if we consider the difference of these, and if it comes out, if it is actually fixed, if it is a fixed value, a constant value for all times, for all t's, if this theta at time t minus theta at time t plus tau is actually kind of constant for all times t's, then we say that we have got temporal coherence for time which is actually less than tau. Wait a second, yeah. We say that we have got, should we write this one? I don't think we should need this. So yeah, we have got temporal coherence, at least for this duration tau actually. And if this is actually kind of constant for if theta at time t minus theta at time t plus tau is constant, then we say that we have got temporal coherence, and it should be actually for all times. And this is it. I want to talk I think about this topic. They are slightly confusing anyways, to be honest, but we should actually pay more attention. Anyways, let me go to the next property of the laser beams, which is actually um, about short pulse nature of the laser beam. So for that, I need more space, so let me erase some of the stuff on the board. So we discussed about monochromaticity of the laser beams, and we discussed about coherence of the laser beams. And now I want to go into, this is coherence, and the third thing is short pulse nature of the laser beams, short pulse output. So the output of the laser beams can actually be pulsed. Of course, the historically first laser, which was a ruby laser, itself was actually kind of a pulsed laser. And this short pulse can be achieved with the help of two processes. The first one is called Q switching, and the second one is called mode locking. So in Q switching, what happens is in the laser cavity where we had these two mirrors and then active medium inside, we actually kind of change the reflectivity of one of the mirrors from being perfect to less perfect value. And when the reflectivity is more, of course, we don't have anything in the path of the laser lasing photons. But when we need this reflectivity to lower value, or maybe lesser perfect value, we put something called a shutter. So when we put a shutter, the quality of the resonator, we can call this thing as optical resonator, and this resonator will actually decrease. And when we don't have the shutter, or when we remove the shutter, then the quality of this resonator will be actually very high. So we are actually switching this quality of the quality, actually kind of abbreviated as Q here, and we are switching the quality of the resonator here. And when we have the quality as a lesser value, then because of the pumping source here, we actually can create more population inversion inside the active medium. And when we suddenly release the shutter, that means when we suddenly allow the quality to grow perfect value, then we start having lasing action taking place, the stimulated emission starting here, and then we have more amplification of the lasing photons, and this process will give us kind of very narrow pulse, narrow width pulses as output of the laser. And through this process we can go as narrow as pulses of nanosecond width, few nanoseconds width. So anyways, this is about quality switching process of the laser, giving rise to very narrow, very narrow pulse as output of the lasers. And for the second process, which is mode locking, we know that a laser resonator or the laser cavity will actually support longitudinal modes satisfying with this condition, lambda, n into lambda sub n divided by 2 is equals to L. So all these lambda n's, lambda 1, lambda 2, lambda 3, etc., they are called as the longitudinal modes, and the separation in the frequency domain between these, we can convert these into even frequencies, right? So because nu sub n is equals to c by lambda sub n, so if we convert these lambdas into news, and if we actually find the difference between nu sub n minus nu sub n minus 1, we get it is as 2 by c by 2l as the value. So at with this separation we start having nu 1, nu 2, nu 3, etc. So if you somehow make the phase difference between the waves of nu n frequency and nu n minus 1 frequency, which we can designate as theta n and theta n minus 1 as a constant value. So this is actually constant. Then we can actually have kind of constructive adding of all these modes. So if we make the phases of the different longitudinal modes of the laser as locked, we're going to lock the phases of these waves. That means we're going to create a condition where the difference of the phases of those waves as constant. Then we start having output as pulses. So the output of the laser beam will actually emit short pulses when we achieve the locking of the waves, longitudinal wave, waves of longitudinal mode frequencies as locked. So anyways, this is the thing which I want to talk in the mode locking section, and here we can achieve pulses as narrow as a few femtoseconds width. So after this I want to go into the next thing, which is actually directionality of the laser beams. So let me put this number 4 here, property number 4, and this is about directionality of the laser beams. So the laser beams are actually pretty much unidirectional, because the output comes through the second mirror, the right side mirror, which is actually partially, 19.9% reflecting, and the other one is 100% reflecting. So output comes always through this side of the laser, and it's directional because we gonna actually only amplify the photons inside the active medium, which are normal to the surfaces of these mirrors. So it is because of this condition of the photons which are normal to this only will get amplified, and the widths or maybe only only um, photons which are going through uh, active medium will get amplified. So even the width or maybe width also is governed by the size of the active medium. So which is actually kind of only this much. So we're gonna have only the output of the laser beam coming only through this. As this much of the size of the with this size of the thing. So yeah. So the laser is pretty directional because of the arrangement of the laser cavity. Whereas if you consider an incandescent bulb, it can actually give light in all directions, all possible directions. But this one gives unidirectional output. So the next property which I want to talk about is intensity of the laser beams. So intensity is usually defined as energy of light, energy divided by time into area which you are considering normal to the propagation of the laser or the light beam. So if the light beam is going like this, then if you actually pick up some unit area of course in the path of the laser beam, then if you actually observe the number of photons or maybe energy of the light per second, then that's what we call as intensity. And for lasers this value can go very high, very huge value, because the beam is coming only in small area, a small area which is supported by the active medium of the laser. And of course as it is coming pulsed also sometime, then it can actually give rise to strong intensity, very large values of intensity, even the intensity which can break the air. So if you go to a pulse laser lab, then you will see kind of tup kind of noise that's coming because of breaking of air. So it is actually creating ions, ionization of air, which give rise to some kind of thing called plasma inside the lab. So intensity of lasers is pretty huge because of the fact that it can be pulsed, and all the photons are actually concentrated in a small area which is coming out of the laser. Small area beam. So this is it I want to talk in this video, and I hope I made some useful points here, and I will meet you next time with some other video. Bye bye for now.